Alright, here we are. We're on 1-4, and congratulations on getting through the first three lessons. I'm hoping everything's working well for you. Remember, if you have questions when you come into class, write up on your board your question and your name so I can hunt you down. Also, pay attention to when we have mini lectures scheduled so you can join in on that if it's something that'll help you answer your question. If you've gotten your question answered and your name up on the board, go ahead and erase it if you've got it. No reason to leave it up there. But let's get going with this. This is 1-4. It's picturing expressions. And, you hear picturing, you're thinking about Rembrandt or Van Gogh or, well, I don't know, whatever you think of when you think of a picture. But we're talking here in math, so often we talk about picturing, we're talking about graphing. And we're going to talk about different ways of doing that. So you want to, as before, read through the lesson. This is 1-4. You want to read through this. You want to know what the vocabulary is in the lesson, so when you hear these words later, you know what they mean. So that'll be part of your assignment. Also do the covering the reading and the applying the math section. The solutions will be available to you. Remember to, where needed, to show your work, show the steps that it took for you to get to your answer. Okay, let's take a look at the vocabulary real quick. We've got a couple of bits of vocabulary. We've got the term scatterplot and domain of a variable. Scatterplot, they talk about it down here at the bottom of page 27. This carries on into page 28. What's important here in a scattered plot is there's no line connecting the points. And that's because, as in this case with the toothpicks, it doesn't make any sense. You have a whole toothpick or you have no toothpick. You don't have a half of one or a quarter of one. So that's why these are called integer solutions. And it's a scatter plot, no line connecting them. So the domain of the variable, and the domain applies to the x variable. The domain for this variable, the x, is the sequence 1, 2, 3, 4, whole numbers, positive whole numbers, or counting numbers, whatever you might want to call them. Now there are other types of graphs, and that's where this next piece goes, is connected graphs, where in this example it shows about there's a mileage problem. Yeah, you could have gone a half a mile or 3.5, or you could have gone for 2 hours or 2 hours and 1 minute. So there are fractional parts of this, and this is a measured thing. Time is a measurement, distance is a measurement, and both of those are available to be graphed as a line. You can connect the points between the coordinates. Take a look at the page 29. This is a fairly short read. A couple of things to cover here. One is the common domains of variables, and it gives you what they're called, whole numbers, integers, real numbers, non-negative real numbers. These are ways we could describe different domains of a variable. We have a description of it, and it gives you some examples. Now, one of the things I want to point out, it kind of gets overlooked in this lesson. It's important that you know it because it's going to come up again, and that's what's called set builder notation. Set builder notation, you're going to see, is right down here, and it's this bit right here that I just highlighted. So that's a bracket, and it's basically read as the set of numbers x such that x is greater than or equal to 0. Or we might say this as x such that x is greater than or equal to 0. You see here an alternative way of writing it. I would prefer we go with the first one, but this is what's called set builder notation. When you see it again, you know we've talked about it. Okay, I'm going to go ahead and get into some guided examples for this lesson. Great. Okay, here we go. We got example 1. This is a guided example. Again, this is not an example that's in the book, but it's in addition to those. So you have 2 sets of examples. So here we've got a situation, the 2 steamboats, the Robert E. Lee and the Natchez. raced, and we've got their distance at 1,218 miles. We have an average speed of the Robert E. Lee, approximately 20 miles per hour, and we're going to fill in a table of values to calculate the Robert E. Lee's approximate distance from St. Louis each hour after leaving New Orleans. So we want to take a look at these categories. We've got hours of racing, and that's pretty easy. We'll go with, how about 0, because then we got a starting point, right? So 0, and we'll put in 1, 2, 3, and then we'll put a variable in here, which is h, some unknown number of hours. Well, we know how far away the boat was at 0 hours of racing. At 0 hours of racing, it was still in St. Louis. It hasn't left yet. So that's pretty easy. We got 1,218 is the calculation and pattern. Basically, I'm started at 1,218. I added in whatever kind of mileage happens after 0 hours, which is nothing, and I'm at still there. And so the remaining distance is the same as the calculation and pattern. Now, when we say calculation and pattern, we're looking for something that helps us to see what happens as we move along here from 1 to 3 hours to h hours. So we can write a pattern down, not just an instance. So we're looking for our instances. So the calculation here in 1 hour, you started at 1,218. So that's how far away it was to start. In an hour, it's gone 20 miles. So it's 20 miles closer. So I subtract that. So minus 20. And then that gives me the remaining part of this, which is, let's see, 2 minus that, so 1,198 miles. So now we got 1,198, and I'm getting offline here, For 2 hours then, and this is where we can be a little clever with our pattern. I got 1,218, that's what I started with. You'll notice I didn't take this 1,198 and subtract another 20 from it, because I want to find out what h is, where I don't know what the hour before h was. All I know is my starting point and then whatever pattern exists. So what happened here in 2 hours is I had 1 hour at 20 miles an hour, and then another hour at 20 miles per hour. So, okay, so now I've got this 1,218 minus 20 minus 20. Let me fix my lines here. And I subtract, this was already minus 20, so 1,198, so another 20 would be 1,178 miles. Now I'm going to do the same thing here in the 3rd hour. I have my starting point, 1,218 miles. I subtract from that my 1st hour, my 2nd hour, my 3rd hour. And now I'm at 1,158 miles from St. Louis. So does this inform us about what could happen here for h hours? So I think I can look at this. So I've got in the 1st hour, I have 1 times 20 miles per hour, 20 miles per hour. In the 2nd hour, I've got 2 times 20 miles per hour, and then this one I've got 3 times. And so it appears that I'm using my hours of racing as my multiplier to do my subtraction. So I got 12,118 minus 20 miles per hour, times h hours. H Hours over hours cancels. I'm left with miles. This is miles. And now I have my pattern, and my remaining distance would be given if I only knew what h was for this particular problem. Now what we want to do with this is to take a look at it as a plot. So you want to go into your graphing calculator and get this information in there and try to create some kind of a graphic about it that would help us understand what's going to happen as time goes by here and what this mileage would look like. Okay, now let's take that data we had from the previous work and we're going to see what the picture looks like for that. So we've got the Robert E. Lee, we've created a pattern for it, and now our picture in math is going to be a graph. So let's make some graph paper here, make it a little bigger so I can deal with it. And now let's take a look at how this would plot out. If time is generally our independent variable, and then whatever happens as time transpires is our dependent variable. So the independent variable, our hours, is down here, hours, and our dependent variable, which is distance, and that's not just any distance, it was the remaining distance. So distance in miles, and this is our time in hours. And so at 0 time we were 1,218 miles away. So, and then at the end of time, once we get out here and it's traveled the full distance, it's now gone 1,218 miles. So that's a really huge graph, and we don't necessarily need to graph that whole thing to get a sense of what's going on with it, but instead we could graph it in a way that would give us an indication of what's going on. So if I go up here, and let's see, we'll go up, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 10, let's go up 10 spaces. And we'll make this 1,220. And so our first point is going to be right in there, just below 1220, and that's at time 0. In 1 hour, we've reduced that time, and so I'm going to do this in tens for right now. So this would be 1,210, 1,200, 1,290, and then this is 1,280, 1,270, 1,260, and 1,250. So we've got this kind of these big categories here. And this was 1 hour, 2, 3 hours, 4 hours, and then we'll see where we go from there. And so our second point was at 1,198, so just right in here. So that's 0 hours, 1 hour, and then I think this looks pretty linear because it didn't change, right? So this is at 78 after 2 hours, and at 3 hours it was 58. And I'm pretty sure I could speculate about that. So that would be at about 48 for this one. But we haven't measured that yet, so we'll stop right here. Now, is this a connected line? The answer is, well, yes it is, because it's going to be a straight line. And we can draw a straight line down through all these points, and we get our line. Now, you'll notice I've kind of left some space here at the bottom. I've left a lot of space here at the right. And that's because we want to look at what's going to happen at the end of time. And we're going to create a discontinuity in the graph. And to do that, we'll make this a nice bright color. I'm going to put in a little mark here to indicate that I'm making a jump. And what that's saying is that as I cross this, I'm moving off of this scale and onto some other scale. As I cross this one, I'm moving from this scale to another scale. And I'm going to go ahead and put another point in there. That would be an indication of our final arrival. And I guess the question I would ask is, do we know how long it took for the 1,218 miles to elapse? Well, how many hours did it take for that to occur? And I wonder, could we figure that out from our calculation? And I suppose we can. At the end of time, the distance remaining is 0. Let's take a look at that. We'll do a little let's do a little calculation here off to the side. So I went to 1,218 minus 20 times h. That's our pattern that we got. And this equals 0 when it's finally arrived. So we can solve here for h to figure out what's going on. And let's see, we want to isolate things on both sides. So I'm going to add 20h to both sides. So I get 1,218 minus 20h plus 20h. That equals 0 plus 20h. I've got to do to both sides of the equation. I did this here, I do it there. Well, 20h minus 20h is just 0 h's, so that's 0. So I'm at 1,218 minus 0 h's. And 20h plus 0 is just 20h. It's 20h. And 1218 minus 0 is just 1218 equals 20h. And now we divide 20 into 1,218. And I don't know, can somebody figure that out real quick? Grab a calculator if you need to, or do that longhand. See what you can get there. So let's see, 1,218 divided by 20. That gives us, oh, not quite, just a little over 60, sorry. So let's see what we did here. We have to divide both sides, so that would be 1 over 20 times 1,218 equals 20h times 1 over 20. 20 over 20 is just 1. That leaves me with 1h. I don't write the 1 there. 20 goes into 1218, 60.9 times, or our answer is approximately 61 hours. So now we've got a value. We can plug that in and just kind of, for completing our graph, we can go back in here to this graph and say that out here, I'm going to say this is time 0 here, and we'll just go ahead and put it in right after this bracket. And so we'll make that 60. This will be 70. Need a little bit better pencil, and right around in here. I don't like that. Do you like that? I don't. We'll just obliterate that, and we'll make our point right about here. Now, we really can't connect these points because of this discontinuity that we have in the graph. It makes no sense to have a line drawn in between them. It would just create a bridge. Well, that's it for that example. Hang on.